Anyway, it's a pleasure to have Pei-Ying back actually. So Pei-Ying got a PhD in 2015 from National Central University, and then she did her postdoc here in SIA for 3 years, 2015, 2018, and then she's now at ALMA ESO, and she's going to tell us about well, we can read, I suppose. Circumnuclear disks. Let's please welcome Pei-Ying back.
Okay, thank you very much. So today I would like to, can you hear me? The people in the backside? Okay. My recent studies Galactic Center, and so this is a project that I was working on in the recent years. The larger scale gas flow from 20 parsec to 2 parsec. And when I was in Sgr A, I was working on these 2 projects. So now I'm working on this most project using all my data in job. So here is a quick overview of the Galactic Center. This is the artist's illustration of the Milky Way Galaxy. Our Galactic Center is located about 8.3 kiloparsec to the center of the galaxy. Because of the AGN field, there are a lot of dust and molecular gas in front of us. So the center of the galaxy is almost totally obscured in optical wavelengths, and we will have to go to other wavelengths, for example, like infrared or high energy wavelengths to see through the structure of the center of the galaxy. So within a central 400 parsec, the pinkish color shows the distribution of the molecular ring or central molecular dome. So it is this ring rotating with respect to SGA star, which is the dynamical center of the Milky Way. So within this larger scale ring, we have another small ring with size of about 2 parsec, shown by these black contours. We call it circumnuclear disk or CND. So the zoom image is shown here. The CND is a molecular ring or torus rotating with respect to SGA star, and within which there are 3 arcs of ionized gas streamers inside of the CND. Because the center of the galaxy is the most closest supermassive black hole to us, so this is the best target to study the detailed structure interplay between the gas and supermassive black hole in galactic. So here I would like to address some important questions. First is the lifetime of the CND. Because the structures is so close to the supermassive black hole, so you will expect a huge tidal force this year. If the gas density is not strong enough to be gravitationally stable, then the structure of the molecular structure will be totally disrupted. So we will have a short lifetime transient structure of accreting material in the supermassive black hole. So determining the density is an important issue to understand the life cycle of heating material close to the supermassive black hole. And the rush limit at radius of 2 parsec is 10 to 7 cubic centimeter. This is a hydrogen. This is the molecular hydrogen density. So this is threshold. If the gas density threshold is lower than this rush limit, then the gas will become gravitationally unstable. And the second question is how do we interpret the transition between neutral phase to an ionized phase? Whether the accretion flow the transition is very sharp or they have any connection, this is still unclear. But understanding the correlation between this ionized feature and this neutral ring is important for us to understand the structure of the accretion material. So I would say the CND we observe in our own galaxy, we can treat it like molecular torus in the external galaxy. So this kind of a CND-like structure is not only observed in our galaxy, but also in external galaxies, from 10 to 100 parsec scales. So this CND may be a detective molecular torus or supermassive black hole, and it's also a very important and critical role to understand how do we link the central accretion material to the central black hole and host galaxy. This is a critical point to link our understanding of black hole feeding to the host galaxy. What is the correlation? What is cascading structure, the inflow structure in this region? So when I am talking about transition from neutral to ionized, it doesn't mean we want to know the correlation between the neutral material to this very nearline region or ground-line region observed very close to supermassive black hole. But I would say it is a phase transition of this neutral torus from inside to outside. The temperature is getting higher and higher, and part of the gas is ionized. So we are talking about the structure here. Okay, so here is an example of the CND observed in several galaxies, NGC 1019, 1068. This is observed by ALMA. So this high density tracer reveal a dense torus, not torus, but just rotating gas cloud with size about 10 parsec. The black hole is located it's labeled by the black holes, but the black hole mass is 10 times higher than NGC, 10 times higher than Galactic center. So it will be interesting to understand in the future what is the physical parameter science, formation mechanism, and also like kind of the CND like structure with different black hole mass of types. And because these help us in different formation mechanism like energy or pressure of the clouds here. So although the Galactic center is very close to us, but because of the AGR view, the data is usually suffer from tremendous foreground absorption. Here's an example. This is a longitudinal galaxy diagram of the molecular gas distribution in the Galactic center. So here this is the CO1 to 0. This is a very bulk molecule, and this is dominated by many low temperature and extended gas. So you will see there are a few black stripes here. This is caused by the foreground absorption. So, but if we go to higher excitation line, like CS21, then you will see these foreground absorptions here. So this tells us that we need to go to higher excitation line or higher density tracer to reveal a more reliable structure of the Galactic center and to analyze their genetics or physical condition. So we made a few new observations with single dish and interferometer to with this CS molecule, and we did several studies using our data. So the first few problems I would like to understand is whether the CND is a transient structure. That is the lifetime of the source of field to supermassive black hole, and also to understand whether the CND and how it is linked to a host galaxy. So this is a paper presented by Miguel Legalpolis. So this is a very great paper. They have a really amazing data set. They did a very comprehensive analysis and derived the density of the gas densities of the CND 3. So they conclude that the CND is transient nature. That is, the lifetime of the CND is shorter than 10 to the 5 years, because the gas density is between 10 to 4 to 10 to 5 cubic centimeters. So this is apparently lower than tidal threshold. But this is a single dish observation, so they are probably looking at different structures, and we will go back to this later. Okay. So even though the tidal force is so strong to make the CND short life, but we know that we have learned that the CND is not isolated, but connected with the nearby clouds. There are a few streamers shown by the yellow contours. This is a streamers revealed by ammonia molecule. So these streamers coming from the Galactic disk is apparently interacting with the CND, so suggesting that even though the CND is short-lived, but it can be fed by the external environment. But this is a very dynamical process. So the previous observation is important because theoretically we believe that the formation of the CND is proposed. One possible proposed scenario on CND accretion formation involves tidal streaming of the nearby clouds within the rotating Pei-Ying star, and the clouds envelope of the clouds is stretched and moves forward and settling down in CND because of the partial completion of angular momentum. But there are tidal degrees surrounding this CNDs. So discovering and starting the tidal degrees surrounding this torus is an important topic to understand the feeding process, the feeding story of the ring surrounding rotating with respect to supermassive black hole and to link this ring to the external galaxy. So here, the tidal degrees of the past feeding process was already marginally imaged by SMA before. So you see this very noisy feature, extended noisy features labeled by the red circle, marginally detected. So our new SMA map, a larger map, we extend the mapping area. So we reveal that these filaments, these remnants, these tidal degrees are actually multiple elongated filaments surrounding and correlating with the CND. Pretty similar to the simulation made before. But unfortunately, because of the SMA map, we do not recover the missing flux. So actually we lose a lot of structures. So we also observe this target with single-dish telescope made by November 55-meter telescope in CS transition, and we have a cross check compare these two structures. So here the contours are the SMA map of the CND and the streamers. Over here, overlay on the single-dish map shown by gray image. So from single-dish image, we can extract more extended filaments associated with the tidal degrees. So we expect the kinematics of these features in the longitude and velocity plot. So we extract spectra along this yellow line, and we extract the spectra, the velocity information. We have the position and the velocity information of these two sides of the CND. So we found that in our extended emission map, we find that the streamers are actually connected and originated from nearby clouds in the galactic center. So this confirms that the CND is not isolated but connect to the galactic disk. And it's pretty cool here because we will be able to say that this accretion material has some kind of a kinetic correlation or origin 20 parsec further out. But this kind of inflow structure is cascading structure. So these streamers shows progressively higher velocities when it approaches to the center, and suggesting that this gas is speeding up when they are moving toward the center. So for a more proper kinematic analysis, we need to compare the velocity information with model. The model here is capillary rotation curve. So here we extracted spectra along the ellipse here, and we make along the ellipse here. So we have the velocity information as a function of a phase angle of these structures. So this is a phase angle, and this is the velocity information. So 4 models will overlay in the plot. So this is a capillary rotation without info and with info velocities from 20, 50, and 70 kilometers per second. So that what I would say as a radial motion instead of the tangential motion. So we find that the data cannot be explained by pure Kelvin rotation, and we need additional radial inward motion to explain the data. So if we consider this radial inward motion as inflow velocity, then the motion of these streamers, we need 10 to 25 percent of the rotation of the radial inward motion is 10 to 25% of the rotation to explain the observed kinematics. So that means we are observing these streamers. Well, we extracted phase diagram not only at the circle, but multiple circles at different radius. So we found that these streamers are actually not only co-rotating with the CND, but gradually merge with CND from outer part to inner part. So it's kind of a accretion process here. Okay. So, but in conclusion, we were able to derive the mass filling efficiency. The mass filling efficiency is about 2% of these external streamers, about 2% of the CND mass. That means the filling mechanism through the tidal stripping is not efficient enough to sustain the light of the CND. But this depends on the condition of the microclouds nearby. If the more massive clouds is captured, then we will have a higher efficiency here. But I would expect that the efficiency is about 3%. So for a 10 to 6, 4 million solar mass supermassive black hole kind of sort of relatively compared to AGN or more massive galaxy, I would say all these processes are relatively slower or less efficient than higher massive, than more massive galaxies. So the physical conditions are pretty different.
Just one question. So here, feeding efficiency is onto a CND.
Yes. Yes. And this is a dynamical process because the whole Galactic is rotating. If the microclouds is away, it's moving away, and there's no massive microclouds in the next streamline, then there's no feeding. So this kind of what I can say is this kind of feeding process is pretty dynamic, and it would be great if we have a simulation in the future to play with the parameters. Okay, so the next problem is I want to understand the transition of the accretion flow from neutral to ionized gas. So contours shows the molecular CND, and this color shows the mini spiral of these ionized streamers. We call mini spiral traced by partial alpha line imaged by HSV. So the idea is that we have when we do this project is if the mini spiral is formed from the CND, then the partially ionized particles immersed in the neutral ring can be charged or magnetized. So if we observe magnetic field lines, then we can probably say something about accretion flow from neutral to ionized gas. Then it would be very interesting to do. Here, this is the dust continuum emission made by Sophia. So you will see both the CND, both the neutral gas ring and this ionized gas, the plasma will observe simultaneously in dust continuum emission. So if this dust emission their magnetic field, and then we can try to use the polarization to do something if they are magnetized. So here, this is a quick view of the magnetic field structure in the Galactic center. The blue segments are the magnetic field lines traced by stellar polarization. So you will see the orientation of the B field lines are perpendicular to the disk. This is a Galactic disk, perpendicular to the disk, but gradually transform to parallel to the Galactic disk. So we can see this trend more clearly in this plot. this is the B field position angle is a function of galactic latitude, and this is the disk. So 90 degree means parallel to a disk, and 0 and 180 means perpendicular to a disk. So we can see a clear trend that the field line is transformed from toroidal field to toroidal field. This is how we interpret the observation. The initial toroidal field, larger scale field. You will also very often see this larger scale toroidal field in plot map. The initial toroidal field at larger scales has been proved exmosally and radial component by the structure in the disk because there are more mass here, so the gravity will be able to drag and catch the magnetic field line toward the disk. So here, this is the previous magnetic field line observation of the CND at 100 micrometer. The segments are the dust polarization. This is the E vector. So the magnetic field you need to rotate 90 degree, and contours are the 100 micrometer dust continuation of the CND. So you will see the magnetic field orientation is parallel to the CND. It's parallel to the CND, suggesting that the field lines are aligned with the CND. So this is a happy result. So to explain the previous dust polarization, the magnetic field configuration in CND, Waddell et al. They applied a smooth sticks model of the CND. This is a rotating CND, including the big field line, and actually symmetric magnetic field line where initially polar field similar to consistent with what we observed before, and the initial polar field is able to straight and differentiate into the differential in disk and pull the field line to toroidal field. So in this model, the predicted B field lines shown by these thin segments can explain the observed magnetic field configuration in the CND pretty well, very reasonably well. The thick lines data and thin line is model. So the most important thing that we note in this model is the radial component and the azimuthal component, B field component, are stronger than the vertical component. That means the inflow, the B field is able to remove the excess angular momentum of the gas and help the gas inflow within the disk. So B field line, the magnetic field is definitely doing something here within the central deposit of the Galactic center. So then the next step is we try to understand since the B field lines is important in the CND, then whether the B field lines is also important, is also some connection between the CND and also the mean spiral. So this is the blue segments are the duplicate model. So I overlay the B field model on our observation. So the CND is labeled by is a gray color, and the mean spiral traced by 6 centimeter continuation is shown in pinkish contours. So surprisingly, that we found the B field line is not only able to explain the geometry of the CND, but also the curvature orientation of these ionized gas streamers. Then we want to ask whether the same B field coherent field exists in this region, and whether the B field strength is higher enough to guide the partially ionized gas streamers in this region. Then this will help us to understand and explain the geometry of the ionized streamer here. That is the B field can sort of related to the geometry of the inflow structure here. So we utilize the JCMT archival data to get the data of the magnetic field, and the JCMT data has 20-second resolution and shown by these yellow segments. So to compare with the JCMT data, we also took the spiral data, 6 arithmetic polarization data, overlay with the red segments. So these red segments tells us that the magnetic field is toward in toroidal configuration and in parallel to the larger scale magnetic disk. But high resolution JCMT data shows more subscale structures associated with the cloud itself. So here is a comparison between the model and the data. So here the blue segments are data, red segments are model. So this is the magnetic field configuration of the CND, and this is the data of the mini spiral. And this is the data, the B field position angle, and the model is a function of the phase angle of the CND. So we find that the same model is not only applied to the neutral CND, but also the mini spiral. So this is a very interesting result because it tells us that there's a coherent field in this region. And to explain the observed B field geometry, we need additional radial info velocity. This is 10 to 25% of gravitational velocity here to explain, to create our best fit model. So this is really consistent with the previously spectral analysis. So to quantify the dynamical importance of the magnetic field in CND, we compare the plasma parameter. This is a ratio between the thermal pressure and magnetic field pressure. So we do in 2 ways. First, from observation. So we have information of the thermal pressure, and we compare it with the known magnetic field strength to get this parameter. And the second way to derive this plasma parameter is to go to the model. So the best fit model will also give us the best fit plasma parameter. So this plasma parameter is about 1. That suggests that the B field is important and can help to guide the motion of the gas, of the partially ionized gas from CND to its inward. So that means the structure of this accretion material it is not random statistically random, but they are under some kind of physics. We can sort of predict, if we know the geometry, the magnetic field configuration, we can actually predict the geometry of infall here. However, the B field pressure is high enough to guide the gas, but the rotation, gravity still dominate here. So the B field strength is not able to drag or slow down the rotation of the gas. So it does a little effect on the gas inflow here. Because the ratio between the rotation of the ring and the ratio of the outward velocity is about 13. So this means the gravity is still dominant in this region. So this is our using the archival JCMT data, we firstly found the link between neutral and ionized accretion material here, and we compare the relative importance of gravity and magnetic field here in this region. So we think that the magnetic field is a pretty good tool of footprint to trace the footprint of inflow from neutral to ionized gas here. But But unfortunately, going to external galaxy, the resolution is probably difficult to trace that. Okay, here. So this is the last part I'm going to tell you. It is my recent studies of the in this region within central Galactic using ALMA CS. So these are the problems I would like to ask: whether neutral galaxies can survive within central 0.5 parsec. This is because in the previous map, you don't see a clear detection. You see there are hot gas, ionized gas within the cavity of the CND, but you don't see a clear existence of neutral gas within the central black hole. We want to understand whether neutral gas still plays an important role on black hole fitting within the central 0.5 parsec. The second question is, stability of micro clouds. So it's a competition between the black hole feeding and star formation, because the micro clouds can be used for star formation, and once they are used for star formation, it is competing with the black hole feeding. Okay. So the difference between all this data set, the difference between this project and previous project is scale. This is the archival ALMA data toward in the CND. So in this 1 arc-second resolution map, the CND was resolved to sub-parsec microcloud cores in the CND. So this molecular cores are relatively denser, smaller, and we want to know whether this denser cloud, different from the previous single-dish observation, whether the densities, the new determined gas densities are higher than Roche limit. So that's why we need to go to ALMA. So this is the result. So this is a project that I started when I was here, and we observed the CND and the streamers around using different 5 transition of the CS lines. So this is the on-source time. So total on-source time is 88 hours. So this project can be finished in 1 semester, and you can see that ALMA is pretty powerful to conduct this large-scale mosaic study. So here, this is a comparison of the previous SMA map. We can see, consistent with the previous understanding, you can see the CND, because of its high excited nature, then we can see it's more getting clearly toward the high jet lines because of this high excited nature. So this is the first thing you can see in this image. And for more information, I will tell you later. So the data reduction is extremely difficult. It's super difficult, very difficult. But I'm going to skip the detail how to reduce data, clean data, and combine data here. If you are interested in combination of interferometry and single-dish data using ALMA, we can have a chat if you are interested. So this is a comparison between ALMA and SMA map. Honestly speaking, I would say the SMA map is already pretty good compared to the previous single-dish map. So the high resolution given by ALMA tells us that these micro clouds will resolve into filaments, multiple filaments-like structure within this block, showing the lower resolution SMA map here. So it shows much more turbulent and filamentary, and also coexisting with quality structure here. So combine the powerfulness of this map is we have a single-dish information, and the previous SMA map we don't have single-dish information. So recovering the extended flux, we resolve and detect the surviving neutral gas within 0.5 parsec of such A to such A star, such A star is labeled by zero growth. So the neutral gas is surviving within 0.5 parsec, and the single-dish data field the depth of the short spacing also reveal relative the central tension between the central concentration and also the CND here. So this is the difference between with single dish and without single dish. This is the image. This is the same region, the region image by Moser and all, but 12 meter only. So in there, well, that map is already very good enough. You see, resolve the structure of the neutral gas within 0.5 parsec. But because of the leaking of the short spacing, so all this extended vision is gone. And their map has a smaller field of view, so we are not able to study the connection between the micro gas within 0.5 parsec to the CND. Okay. So here, this central concentration, this is an integrated density map, and this is a velocity map. Although the velocity structures are pretty complicated here in this region, but overall we see the central concentration is correlating with the CND in the sense, and it has a relatively north-south orientation. But it's interesting that to see whether this thing is connected to the CND. So we would like to study how the Milky gas is channel pass through the central parsec of the galactic center. Because in the previous study they conclude that this central Milky dark cloud is totally disrupted from the CND and fall to the center. So we'll be able to analyze the connection. So we analyze the kinematics of the central concentration. We compare it with the polarization curve. But surprisingly, we found that the geometry of the central concentration, the Milky gas within central parsec of the SGA star, the incarnation, it has very different orbital information from the CND. This has a relatively phased-out structure with very low inclination, 10 to 20. But the CND is highly inclined, 70 degrees. So this raises ambiguity that how do we get rid of the angular momentum with such a different inclination from CND to the central parsec in a short time scale? It is a few thousand years. So this is apparently impossible. So so I think the different inclination, different geometry tells us that the structures analyzing the structures in this region tells us that the different epoch of accretion history in this region. So this is probably the earlier info event, earlier than the CND. So it is like the older inner disk. So I'm trying to, because it is a phase-on geometry, so it will be very interesting to compare the motion, gas motion, the motion of the gas, and to the stellar kinetics. There are massive star clusters in the same corresponding region. So it will be interesting to have a look to compare the accretion history of the Milky gas and to see how it is correlated to the previously observed star formation history. Okay, so the last problem I would like to tell you today is the stability of star formation near SGA star, and the idea is we would like to have a measurement of the physical properties, the densities, temperature information of the Milky core scale, and to see how they are associated, how they are behave as a function of distance to such A star. So this is the distance from such A star. This is the gas density, greenwood gas density. So these two lines. This is a model taken by the previous studies. So to analyze the stabilities, we need an indicator of star formation and also indicator of the gravitational stability. In their paper, they use a G stability. So for Milky clouds, G stability and simply the tidal stability. So for Milky clouds, the gas density of observed Milky clouds, if they are lower than the tidal threshold density, then the gas will be unstable and disrupted by the central potential and will be gone eventually. But for Milky clouds, the gas densities overcome the tidal threshold density, but and higher than G densities, then they are possible to form stars. So this is a competition between the gravity and star formation in a very naive way. Yeah. And between and the shaded area marked by these two boundaries are the gas. They are stable. They don't collapse to form star, and they are also stable. So using the ALMA data, we would like to extract microclouds using dendrogram. And after we have a catalog of individual microclouds, then we use a radiative transfer code to calculate the density and temperature of individual microclouds. So the magenta ellipses are identified by microcloud cores made by dendrogram. So the total number is, but it depends on the threshold density. So there's no single answer about the number of clouds here. It also depends on the threshold in your data set and also the program. Anyway, we have 27, more than 27, 2,700 clouds in this region. And this is just to show you overall structure of the identified clouds using a much higher threshold of the identification, higher than 10 sigma. Okay. So after getting the individual microcloud catalog of 5 transitions, then we will be able to calculate the density and temperature using the radiative transfer code. And this is the result. This is the color. The color represents the log scale of gas density, and in the right panel, the color represents the temperature of the gas. So you will see we will have a 2-dimensional distribution of individual clouds in this region, and we can see the higher density clouds. They are sort of two-phase: higher density, low temperature, or low temperature, high densities. But there are a lot of details here, so I don't have time to mention today. And so you will see the higher density clouds will observe toward the CND and also part of the denser streamer surrounding. So after applying some threshold we have 1,000 about 1,100 clouds used for analysis of the temperature and the densities. And this is a histogram of our feeding of the temperature, log scale of the density, and also count density. So you can see the majority of the clouds have the densities between 10 to 4 to 10 to 5 cubic centimeter. So this is very consistent with the previous CND data, right, made by Miguel. But there are still more substrate structures in our catalog. So to analyze the gravitational stability of the clouds in such A-star, then we use the scalar theory in ionized gas. So we consider turbulence, self-gravity, storm pressure, and tidal forces in this region. So self-gravity and storm pressure are able to hold gas, but turbulence and tidal force tend to disperse the gas. For there are 3 cases. For the case 1, if there's no external pressure or tidal force, then we will have a very general theory parameter to evaluate the relative importance of kinetic and gravitational energy. And the second case is if the turbulence and external pressure are 0, then we will have this is simply the critical density of the tidal threshold density. That is the Roche limit. But for case 3, it's more realistic. To simplify the equation, here we tentatively assume that external pressure equals 0, and we will have a density threshold, the gravitational density threshold here, considering all these parameters except external pressure. But external pressure is not 0, apparently, so we will discuss it separately. Okay, so now we have this equation, and we can draw the line. Then we can overlay our data on this model plot. So, this equation. So the blue line here is this equation, but without turbulence. So it is pure. It's a pure radial density regarding to the tidal force. A yellow line is the radial density related to star formation. But it depends on the strength of the turbulent velocity. So for clouds higher than exceeds the critical densities of certain turbulent velocities, then it will be able to form star. And between bounded by these two curves, the clouds will be stable. But under the gravitation, under the tidal threshold density, the clouds will be dispersed by tidal force. So the next step is we need to project the map of the CND, because we know the inclination of the CND and the surrounding streamers are highly inclined. It's about 70 degrees. But because we already have the orbital information done previously, so we can deproject the map. So this is a projection of the map in XY offset, center to such A star. So the CND is deprojected mainly concentrated at radius of 2 parsec, and the surrounding streamers between 2 parsec to 8 parsec. And this is a zooming image of the central 200 nanosecond. So this is a the tidal. This is a critical density is a function of distance from such A star between 0 to 10 parsec. And so we can see a majority of the cacao cores are below tidal threshold density. So that means they are not stable, and they will become in the future they will be disrupted. But some of the clouds are stable. They are higher than tidal threshold, but they are not massive enough, denser enough to form star. But there are still some massive clouds that pass the threshold. And this more these are more denser clouds that they are possible to form stars in the future. But in reality, there's no observed ongoing star formation in the Galactic center. So some additional parameters, for example, like magnetic field, may have helped here to play a role to support the cloud to collapse. And this is the same plot, but the color is showing temperature. So the important information we can extract from this plot is the critical density, the threshold density, critical density controls star formation beyond 1.5 parsec is actually dominated by turbulence. So the tidal force actually doesn't do anything important here beyond 1.5 to 2 parsec. But within 1.5 to 2 parsec, the gravity increases sharply and strongly prohibit the formation of stars within the central 1.5 parsec. And the second point of information here is, although we see there are a lot of clouds here, but actually they are less massive, and they are less dense clouds. So if we consider the mass fraction, then these clouds that are tidally unstable, they are actually only account 40% of the total mass. This is a lower limit. And 20% of the clouds are stable. So it will be interesting to see how these 20% of the stable clouds are evolved in the future. What is the interaction between the gravity, magnetic fields, and tidal force here to determine the fate of the clouds here. But more massive, the clouds are more important for responsible for star formation. They are 59% of the mass here. So although the numbers of these massive clouds are less, but they are actually more important in this region. So this is a thermodynamic properties of cloud cores in this region. I am not going to describe this in detail, but here is I would like to extract one important information here for you. So this is the thermal pressure of the cloud as a function of distance from such A star, and the ambient external pressure calculated by X-ray emission is about 10 to 6 per cubic centimeter Kelvin. So this means, although less dense clouds, they are not stable. They will be disrupted by tidal force. But it seems to be that this simply tidally unstable cloud is able to be balanced by external pressure. So that means the geometry of the entire picture is will be relatively permanent in sense of pressure equilibrium. So the second important information here is this is a gas density as a function of thermal pressure. So interestingly, we found that there's no high temperature and high density clouds. There's no population. There's no such kind of population. There's a huge debate about the missing population here. For example, we can say if the cooling rate, just the cooling rate is proportional to the square of the density of the gas. So for higher density gas, the cooling rate is much more efficient than the lower density gas. So naturally, we don't see the population over here. And this is important here because except the effect of the turbulence on the star formation, the missing population of the higher density and higher temperature gas also set up an upper limit of the Jeans mass. That is the mass of the stars. So there's no it's less possible that we have supermassive stars form here because of the lagging of the nest of the star formation here. And this is my summary page. So using the data we collected in past years, we analyze the effect of a gravity and magnetic field in the center of the galaxy. And we found that the gravity is an important shaper in this region, but the B fields also help to guide the material in this region. So we used a series of observations such as polarization to study the role of the B field associated with the gas. And also using centralized data, we will be able to analyze kinematics of the gas near such A star. So I would probably leave the summary page to here. But important thing is we still don't have information of a magnetic field within central to polarization of the galactic center, and it will be interesting to see how the magnetic field is acting on the accretion of the gas with in the very center of the galaxy. And we have thermal calibration here to probe the magnetic field lines here. The project was granted, but unfortunately because of the COVID situation, so we are the cycle 7 observation was postponed. But fortunately, I think our project will be possible to be observed next year. The cycle 7 return. So I hope, I don't know. I will stop here. Thank you.
Thank you so much. We have time for questions, comments.
So you found this inner disk here. This thing is from the previous population, previous events, right? So is the density? Can you measure the density of that disk? And is that density suggested it will be gravitationally stable over a long period?
Yes. Because within a central to polarization, all the gas densities are lower than tidal threshold. But we don't know the role of magnetic field here. The role of the magnetic field on supported cloud here. So so magnetic field observation will be able to answer your question.
I have many questions, but a few. First, the info. You are saying that the circular orbit, I understand. But if it is the elliptical orbit, then it looks like the info, but actually not. How to distinguish
No, I cannot distinguish. Because here I say info, but actually what I can say is it is radial inward motion. But I cannot say it is something really fall into the center. I cannot say that. No, honestly speaking.
The last part, but you said there's no high density, high temperature cloud. But is that biased by the line you observed? Because CS is sensitive to the density, but not really sensitive to the temperature.
Yeah, it's another possibility. We can go to high excitation lines like going to the infrared, mid infrared spectral line, but resolution is not good enough. So.
Well, CS is basically capacity optically thick line, so that completely optically, if you observe optically thin line, then and do the similar things, maybe you can.
Yes. Let's see. We will be able to do that. In principle, we can estimate. We can estimate the mass, and we can calculate how much integration we have to do this kind of observation. But I guess it will be difficult. My feeling. Because it's very high. They are very high temperature gas, so even though it is optically thin line, you still need to go to high precision. This is my feeling. I don't know. Yeah, I'm interested in this, but I don't have a good answer for now to continue this problem.
Why CS is a better tracer as compared to H?
Oh, HCS is good, but it depends on the science goal that we are interested in, because HCN it is contaminated by the radiative only. So the emission we observe is not guaranteed. It's collisionally exciting. So if you want to have a more reliable density measurement, then going to HCN will be more tricky. Yeah, because I think they are already vibrational excited HCN line observed in this region.
Is it possible that CS is also radiated?
Yes, yeah. It's also it's also possible, but I think less important than HCN.
Okay, there are no more questions. We can finish it there today. Let's thank Pei-Ying again.